Hello everyone. In this video we will discuss about elastic potential energy. Okay. So suppose we have a horizontal table and on that you have a rod fixed at one end, mass m, length L, cross sectional area A, Young's modulus Y. An external force is applied so that F external is applied so that the rod elongates slowly. Okay, so that the long rod elongates slowly. And say due to this force, this has elongated by a length of small l. Right? Now, when say the elongation was, this is the length, initial length. Say when the elongation was x, you were applying some external force. This external force was to overcome this restoring force, right? Since you are elongating the rod slowly, can I say at this moment it will be equal to F restoring. From Hooke's law, I can write restoring force. This is the stress. That will be Young's modulus into strain produced. Right? So Fr can be written like this. So F external is also this. I'm talking about the magnitude part. Right? Can I say, please pay attention to this. Can I say from here it elongates by a small amount dx. Can I say small amount of work done by external force plus small amount of work done by restoring force should add up to 0? It should add up to 0 because the rod is elongated slowly. So kinetic energy change of the system will be 0. So can I say this is nothing but minus du. So du will be equal to this. So I can write du is equal to, I can write small work done external is F external right now into dx. So if I put the values, right? So now du is this. I can integrate. I take a reference when the body was at its natural length. So can I say at that time elongation was 0. And when elongation becomes small l, that time energy stored is u. Correct? So what we have done, we have considered this to be the reference potential energy. So we are now going to consider this as the reference. So we will shift the coordinate system to here. This will be the new coordinate system. Like this. Okay. So that at natural length, potential energy becomes 0. So this is our new coordinate system. Fine. If you integrate this, it becomes okay. I can write this in this manner. Please pay attention here. I can rearrange this. We know in this situation, in this kind of situation, throughout this rod, stress is same. If stress is same and Young's modulus is same, stress and strain same, right? At all sections, stress and strain will be same at all sections, correct? So can I say this is and A into L is nothing but the volume. So can I say total potential energy by total volume? So this is nothing but energy density. Therefore, energy density du by dv can be written as half into stress into strain. From Young's modulus, I can write stress as Young's modulus times strain. So this will become strain square. Also, I can write strain as stress by Young's modulus. So it will become stress square by Young's modulus. So these three are very important formulas. These three are very important formula, right? Okay, now let us take a look at this question. A wire is hanged and it stretches under its own weight. We have to find out the energy stored. Okay. So say after stretching it has reached an equilibrium state. At a distance of x from the bottom, if I find out the stress, if I draw the FBD, so restoring force turns out to be this. So stress at that point will turn out to be this. We assume there is no change in cross-sectional area, right? We are assuming that. If that is the stress, if I take a small segment here of dx, in that small segment, restoring force will almost remain same. So stress will almost remain same. So can I write energy density is half into stress square by Young's modulus. Du can I say dV is the volume of that segment and that can be written as cross-sectional area into dx, right? So I can write du as if we integrate we will get the total energy stored, correct? So when x is 0, it will go from 0 to L. So U then is equal to so U then will become this is the stored potential energy. Fine. Note one thing. If stress and strain are constant throughout, we can then rearrange like this. And if we integrate, since it is constant, stress into strain, it will be out of the integration, and you can write energy stored is half into stress into strain into volume. So you don't have to perform integration if stress and strain are constant throughout the volume. Fine. If they are not constant, you have to perform the integration as we have shown in the previous question. Fine. In the next video then we will discuss about Poisson's ratio and thermal stress. Thank you everyone.